So today I want to talk about the chain rule. Chain rule deals with composite functions, where we have one function inside another. My favorite image for this is this. I have an outside function, but I also have an inside function. So keep this in mind. We'll come back to her on a regular basis. Here's my example. I have x squared inside a cube. Now I know that by the rules of algebra, when I have a power inside a power, I multiply those powers together. And the derivative of x to the sixth is 6x to the fifth. That's just power rule. Nice and easy. But if I consider this as ugly thing cubed, right? Thing cubed, then I'm looking at just the outside function. And I say, oh, well, the derivative would be 3 ugly squared. But this derivative isn't taken in terms of x. And notice those are different. That makes me unhappy. I've missed something. By doing this derivative, my derivative isn't taken in terms of x. Now, what's missing? What's missing from here to here? Well, in order to get from a 3x to the fourth to a 6x to the fifth, I need another 2 to get from a 3 to a 6. I need another x. And it's missing as a factor, as if I was multiplying. Wait a minute. This derivative was taken in terms of ugly. Ugly cubed to 3 ugly squared. Not in terms of x. But our ugly here, I'll just use u for ugly. Our ugly here is the x squared thing. That's how we put it back in here. If ugly is x squared, then I can think of taking the derivative of the ugly part. And that derivative would be in terms of x. And that is exactly the missing factor I need. Hang on a second. I took the derivative of the outside part, leaving the inside alone and doing nothing else. But I needed to also take the derivative of the inside part. And that's what happens here. So if I want to think of my composition of functions as an outside and inside, I need to think of taking the outside derivative. I also need to think of taking the inside derivative. In a very real sense, I'm linking the two pieces together, thus a chain rule. So I can think of taking the derivative with respect to x of x squared cubed as taking the derivative 3 ugly things squared, but wait, there's more. This extra piece is that derivative of u. Hmm. It's almost like I'm using this u as another variable. Let's think of our function. F of x is x squared cubed. But I really want to think of it as the outside and the inside. So I'm going to think of f of u being u cubed, yes, f of ugly, Although if you really want a FU function, that's a different story altogether. And then I'll think of this u in terms of x. And then this derivative here, that is the derivative of f with respect to u. 3 ugly thing squared. And then this is the derivative of u with respect to x. And if what I really want is the derivative of f with respect to x, I can do df, du, du, dx, and those cancel, don't they? That's where this idea comes from. I chain my two functions together. As long as I can clearly identify an inside and an outside, I'm going to call this the chain rule. The derivative of a composite function. You take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. I like this version. As long as I can tell what's the inside and what's the outside, I'm good to go. Now, in our example with x squared all cubed, that was easy to deal with. But if I had, say, x squared plus 2x minus 3 all cubed, and I wanted the derivative of this, I'd have to multiply that out. And multiplying that out is not trivial. I'll have 9 different pieces to get it. No, I don't want to do that. So let's not. This is ugly thing cubed. The derivative is 3 ugly things squared. Just copy that inside part down. Don't change a thing. But wait, there's more. Order today, and you will also get, for free, no extra charge, the derivative of the inside. What's the derivative of x squared plus 2x minus 3? The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 3 is 0. I didn't even have to do any algebra. I don't have to factor anything out here. This works perfectly. At this point, I would say, are there any questions? You're not here. You can't ask me questions. Pause the video, write down whatever question you have, email it to me, or we'll talk about it next Monday, the 23rd. As long as I have an outside and an inside, I want the derivative of the square root of the quantity x squared plus 1. That's what's under the radical. That's the inside. I can think of the f of u as the square root of u. I can think of u of x as x squared plus 1. An outside part and an inside part. So when I go to take my derivative, ooh, I don't like taking derivatives like this. Let's rewrite that. That'll be u to the 1/2. Now I know how to take the derivative. I get 1/2 u to the negative 1/2. Just copy down u. And now, I always do this in this infomercial voice. But wait, there's more. What extra bit do we get? Derivative of x squared plus 1 is 2x. I'm perfectly okay with you leaving it like that. Most textbooks will simplify. This is to a negative power. Negative powers go in the bottom. The 1/2, the 2x goes on the top. Wait, I have a 1/2 times a 2. They cancel. And again, square roots are 1/2 powers. All of this is optional. If all I want to know is, can you do the derivative? I just want to see this. Can you do the rule? Imagine you were doing something, I don't know, to 100th power. Find the derivative of x squared plus 4 to the 100th power. That's disgusting. I don't want to do the binomial with 100 powers. You imagine writing out Pascal's triangle all the way down to the 100th row? But I don't need to. Ugly to the 100th. The derivative of thing to the 100th is 100 thing to the 99th. Then I can copy in the thing. And now, the extra bit. Derivative of x squared plus 4 is 2x. All done. Sometimes the inside and outside are clear. Here is a function. The part that's the outside is the sine. The part that's the inside, u of x, is x squared. So when I go to do the derivative here, derivative of sine, we just did this. The derivative of sine is cosine. I don't change u. And then I multiply by the derivative of the inside. But sometimes our algebra writes things tricky. How is this function different from this one? Okay, in this example, it's sine all squared. This is really sine of x squared. So here, what's the outside part? Oh, it's things squared. And the inside part is sine of x. But looking at this, you might not see this right away. This is why I said you have to be careful and remember what's the inside and what's the outside. So now if I want the derivative g prime of x, take it in u. The derivative of u squared is 2u. What is the ugly part? Sine of x. And then u prime, but wait, there's more part. Derivative of sine of x is cosine of x. This is why I'm so particular about using parentheses on trig functions, because some people will write the following, and it annoys me to no end. If you write y equals sine x squared, where do the parentheses go? Is that sine of x squared, or is that sine of x squared? See how you didn't put parentheses on the x? Again, this is just good mathematical notation versus bad mathematical notation. So when you're going to write a trig function, you really ought to put parentheses around the part you are making the argument of your trig function. Again, normally I would ask for questions here. Sometimes the algebra we choose to do can be done in several different ways. I want the derivative with respect to t of t minus 2 over 2t plus 1 to the 9th. Now you have a couple choices about how you address this. You could think of this as ugly thing to the 9th, where our ugly part is t minus 2 over 2t plus 1. In which case, when you do the derivative, you get 9 ugly to the 8th. But wait, there's more. What goes here? The derivative of the ugly. Oh, 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 that's quotient rule. All right. We have a top and we have a bottom, so it's the derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. I don't like it, but it works. And remember, as with all our derivatives, unless we have a reason to, I'm not going to bother to simplify. Again, my textbook will simplify. But here's another option. You could take our fraction and distribute the powers. And then you have ugly thing to the ninth over different ugly thing to the ninth. Think of plugging in a number. You'd take the ninth powers before you do the dividing. That means you're doing the dividing last. We work our derivatives in the reverse order. If the last thing I'm doing is dividing, then the first derivative rule I'm going to do is the quotient rule. This is our top, this is our bottom. But when I go to take the derivative of the top, I need a chain rule. When I go to take the derivative of the bottom, I need a chain rule. So I'm going to get an extra factor on the top prime and the bottom prime from the chain rule. And now I can do the quotient rule. F prime of t. F prime of t. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. It's already to the ninth power. When I square, I multiply the powers together. Ew. Is one particularly better than the other? Not really. I think this one sucks a little less, but not a lot. All right. Again, the important part is to tell the inside from the outside. We did e to the x. We did e to the x last Friday. But now this is e to the stuff. I don't have to use the word ugly every time. Stuff works. E to the u. U is 5x. And then our f is e to the u. E to the thing. So when I go to do the derivative, what's the derivative of e to the x? Well, e to the u. Derivative of e to the u is e to the u. So when I do derivative of e to the stuff, I get e to the stuff. But wait, there's more. The derivative of the stuff. Now, me being the person that I am, I don't like to put these extra parentheses, so I move the 5 to the front. But that's just stylistic. You don't have to do that one way or the other. Even if it's complicated stuff. Now, let's put a minus sign in front of that. E to the minus x squared over 2. I promise there's a reason I used this one. Well, then the derivative, it's e to the stuff. So I get e to the stuff again. And now derivative of stuff. What's the derivative of? Oh, that's negative 1/2 x squared. Sometimes I write it down anyway. Then the derivative would be negative 1/2 times 2x, which is minus x. And that's what goes there. Now, the reason I picked this particular function is because of what its graph looks like. Let's graph this. Out come the graphing calculators. y equals e to the negative x squared over 2. If I graph this, it's kind of small. Let's zoom in. Hey, I know that shape. Matter of fact, it usually is a little wider and a little taller in appearance. I know that shape. And if you've taken a statistics class, you know that shape too. That's my bell curve. It's one variation of a bell curve. There are lots of things very related to a bell curve, or a normal distribution, or a Gaussian distribution. If you've never taken a stats course, please ignore that. We'll see it there. But I wanted you to see this curve in the first place. Here's another exponential. Remember, I said we chose e because it had that nice property about its derivative. E to the x's derivative is e to the x. So what if I'm doing 10 to the x? That's not the right base, but this is the one that I use in all the chemistry classes. pH, physics classes, decibels, and the Richter scale. They're all based on powers of 10. I do a lot of powers of 10 in my science classes. How do I take the derivative of this? I can't. The only one I know the derivative of is the e. But I do know that e and ln cancel each other out. So I can take 10 and I can write it as e to the ln of 10. Now, ln of 10 is a number. Matter of fact, I don't know what that number is. I can find it. ln 10. But I just need to know it's a number, right? That's the important part. This is a number. And that makes this function e to the ln 10 to the x. What happens when I have a power inside a power? Right. Powers inside powers get multiplied. So this becomes e to the ln 10 times x, but that's a number. So's 5. We know how to do e to the 5x. That means I know how to do e to this ugly number x. The derivative is e to the stuff times the derivative of the stuff. But the stuff is number x. So the derivative is number. Hey, wait a second. Wait just a second. This that's our 10 to the x. And this is a number. Didn't I say last Friday that when we had the derivative of b to the x, we got b to the x again, and then some constant? This is going to work every time. The derivative of b to the x is b to the x times ln of b. That's where that constant comes from. It comes from the chain rule. Every time. Again, at this point, I would be asking if you had questions. I will use the chain rule connected with lots of other rules. So I might give you a function that looks like that quotient we had earlier, or maybe it'll look like this. Maybe I want the derivative of this. If I want the derivative of this, I have a product rule because I'm multiplying two things together, and I have a chain rule. So first, second, product rule says you take the derivative of the first times the second, then you leave the first alone and take the derivative of the second. E to the stuff, but wait, there's more. The derivative of the inside. The most common version of this that I use is a function that looks like this. Now, why would I have a crazy looking function like this? Well, a function like this has a very interesting graph. Let's change that from 0.05 to 0.5. Y equals e to the negative 0.5x times cosine 3x. Now, if my graph was just cosine 3x, it would wiggle back and forth, up and down as we went. But this e to the minus 5x gets smaller as we go along. Oh, ho, 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 ho. Imagine a swinging pendulum slowing down as gravity slows it down, as air resistance slows it down. Imagine a bouncing shock absorber. I go over a bump in the road and my car bounces, right? I want that bounce to settle down. These sorts of things come up in physics and in chemistry, in reactions, in bouncing objects. This is an engineering result. It's called a damped oscillation. Oh, let's do the derivative. What's g prime of x? G prime of x, derivative of the first. So e to the stuff gives me e to the stuff. But wait, there's more. Derivative of number x is number. Leave the second alone. Plus, leave the first alone. Take the derivative of the second. Derivative of cosine is minus sine 3x. Oh, it's sine of stuff. Chain rule again. Sine of ugly, derivative of the ugly. I put the 3 in front. I put the minus sign in front. I put the minus 0.5 in front. I just did some algebra to rearrange that. But I think this is a really useful derivative. Again, at this point, I would say, hey, what questions do you have? Okay, I had an outside function and I had an inside function. Do you hear that? Oh, wait a second. Oh, there's absolutely no reason to only have one. I can go with more layers. So now I have an outside function, sine. But then the inside is also a chain rule, an outside and an inside. So I have an outside, a middle, and an inside. I have more layers. But I'm just going to peel this like an onion. I'm going to do my outside derivative. Then I'm going to do my inside derivative. But when I go to do that inside derivative, lo and behold, Out pops another layer. Derivative of sine. The derivative of sine is cosine. Leave the inside alone. But wait, there's more. Now I look at the inside part. The inside is cosine of tangent. The derivative of cosine is minus sine. Oh, that's not right. I started to write x. Change this, I leave the inside alone. But wait, there's more. There's the derivative of the inside. What's the derivative? Tangent. The tangent is secant squared. The derivative of the outside, the middle, and the inside. A three-layer deep chain rule problem. You know the problem with this? I don't have to stop at 3 or 4. How many layers deep do you want to go? It doesn't matter. The chain rule works no matter how many layers deep we have to go. And that means that these exact problems could have lots and lots and lots of outsides and insides. How do I know when to stop? I believe the easiest way to know when to stop is if you think of all of these derivatives in terms of what variable we are using. Remember, I was writing f of u, and I was writing u of x, and we were taking our derivative df dx. So when I finally get to the inside, just being an x, the derivative of tangent is secant squared of x, the inside is just an x. I'm doing my derivatives in x. As soon as I have just an x, I can stop. Whew. So there is, in my opinion, a fairly straightforward way to know when to stop. Again, I can put this in the same context as I've put other problems. I would like to know where the tangent lines for sine 2x minus 2 sine x are horizontal. And believe it or not, this particular problem with numbers other than 2 came up in my PhD research. If I'm asking where a tangent line is horizontal, horizontal refers to slope. How do I get the slope of a tangent line? Right, that's my derivative. And a horizontal line has a slope of 0. I need to find the x's so that f prime of x is 0. So I need my derivatives. Let's take a derivative. F prime of x. The derivative is sine of 2x. There's my chain rule. Outside, inside. The derivative of sine is cosine. But wait, there's more. What goes there? Derivative of the inside. This 2 is being multiplied. It stays there. The derivative of sine x is cosine x. Now, I need to set this equation equal to 0. Okay. 2 cosine 2x minus 2 cosine x equals 0. I'm not really happy about that because I got a cosine of 2x here and a cosine of 1x here. And when I work with those together, that really makes me unhappy. So I would much rather convert all of this to just be in cosine of 1x. There's a trig identity here. Remember, I said you didn't need to have a lot of trig identities memorized, but there were a couple I was going to use a lot. I said this way back at the beginning of the semester when we were doing the trig appendix. And the two I said we needed to really know a lot were the double angle formulas. The double angle formulas, sine of 2x is 2 sine x cosine x, and cosine of 2x is cosine squared x minus sine squared x. But there are two other versions of this. One that only involves sine squared, and one that only involves cosine squared. Then everything would be in cosine x, wouldn't it? So if I make this change, my equation becomes 2 times 2 cosine squared. Oh, that's not right. Cosine 2x. Oh, no, that was exactly right. 2 times 2 cosine squared x minus 1 minus 2 cosine x equals 0. There we go. Now it's all in cosine of x. I think I'm going to divide everything by 2. If I divide by 2, I get 2 cosine squared x minus 1 minus cosine x equals 0. Oh, that's a quadratic. 2 ugly squared minus 1 minus ugly. That's 2u squared minus u minus 1. I can do that like a quadratic. That's a quadratic. Here I'm letting u equal cosine of x. Remember that. We'll need it in a minute. This factors. I want a minus 1. So I need a 1 and a 1. One of those needs to be positive. One of those needs to be negative. In order to get a minus, I need this one to be negative and this one to be positive. So either u equals 1 to make this 0, or u equals negative 1/2 to make this 0. But u is cosine of x. What value of cosine, what value of x makes cosine equal to 1? Oh, go back to your unit circle. Cosine is 1 right there. That's the angle x equals 0. Or any multiple of 2 pi. So x equals 0 plus 2n pi n any integer. I want cosine of x to be negative 1/2. Negative 1/2 is over here. That's this angle and this angle. This angle is 2 pi over 3. Or I could add any circle to it. This angle, well, if you go this way, it's a negative angle. If you go all the way around, you'll get the positive version. It's either 4 pi over 3 or it's minus 2 pi over 3. We found them. We found all the possible places where this graph has a horizontal tangent line. By the way, if you look at this graph, you will see sine 2x minus 2 sine x, 2, 3, 1, 2, 3, 0, 2 pi over 3, 4 pi over 3. And it repeats. That's what the plus 2n pi does. It repeats every 2 pi. Now, please notice, there are a lot of very interesting composite functions that get used in a lot of different places. So the chain rule is going to show up a lot. I mean, a lot, depending on what we are doing. One of my more common examples are examples that look like this. Problem number 90. This sort of an equation is called a logistic growth model. And it grows very quickly at the beginning and then settles off. The graph of a function that looks like this, problem number 90, the graph of a logistic function looks like that. And this is a horizontal asymptote at y equals 1. So you see how we grow and then we settle down? If we scale this function, we can look at things like market saturation. We can look at a lake and how much fish it can support, what biological life it can support based on food supply area and other limitations on growth behavior. This is a very useful model. We'll talk about those as models later when we talk about growth and applications of our derivatives. Now, last but by no means least, if you remember, when we spoke and I said we have a product rule and we have a quotient rule, and I told you I really didn't like the quotient rule, I told you this square on the bottom didn't just get thrown out, didn't come out of thin air. Let's take a quotient. If I want the derivative of this, by the quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. But what if I didn't write this as a quotient, but I instead wrote it as ugly to the minus 1 by bringing it out of the bottom? That's a product rule now. That's a product rule. Well, then the derivative is the derivative of the first times the second plus the derivative of the second minus 1 ugly to the minus 2. Chain rule. Derivative, oh wait, there's more. Derivative of the inside times the top. Hey, look, this is a -2. It's going to go on the bottom. That's where that comes from. I didn't pull it out of thin air. This becomes 1 over x squared plus 3 plus -2x times x plus 5 over x squared plus 3 squared. If I want a common denominator, I get exactly this expression. If you hate the quotient rule, you don't ever have to do it. You can rewrite stuff and use the product rule and the chain rule. The quotient rule is based off of the product rule and the chain rule together. I find this particularly useful when the top of my fraction is a number. 7 over x cubed plus 5. If I instead write that as 7 x cubed plus 5 to the -1, well, then the derivative is -7 x cubed plus 5 to the -2. But wait, there's more. A 3x squared. People, I use that so often that one of my former students decided that she was going to buy me a pen, very much like this one that I was just using, and she had it inscribed. You're going to hear this for the entire rest of the semester. The chain rule is one of my favorite derivative rules, period. I also happened to, when I came to Seton Hill, they asked me to do a teaching demo. And the teaching demo I did was on composition of functions and the chain rule. And the problem that I finished with, the very last chain rule problem I did when I interviewed here at Seton Hill, 1, 2, 3, 4, 5, 6, 7, 8, 9 layers deep. 9 layers of chain rule. But it works. This is a very, very powerful theorem. I hope you have a wonderful rest of your weekend. I will see you on Monday. Enjoy.